Alright, welcome back. In this video, we're going over the actual potential graph. Yeah, I know, it's been like 2 months, but I'm back, I promise. Bunch of stuff happened. I basically moved from San Diego back to my hometown. And then my mic broke, so I had to get a new mic. Then my table broke, so I had to get a new table. But here I am, everything's breaking, right? So, big news, I broke 3,000 subscribers, so I am monetized, kind of. I'm like half monetized. Like I enabled donations and stuff like that, but I'm not getting money through ads just yet. But thank you so much. So as promised, I'm going to be revealing how much I make every like 28 days. So like the 28-day period, if that makes sense. So this number you're seeing right here is the past 28 days. So I am worthless. I made a grand total of $0. Let's go. Okay. So some of you, if you've been long-time subscribers or looked at my channel, I made a video on the actual potential graph. That's like one of my earliest videos ever made. It's doing really well. But I decided I can make it better. I can make it better quality and I can make it better. Okay? So that's what I decided to do here. So we're going to take this really slowly because you see there's a lot of stuff going on. If you go to other YouTube channels, you're going to see that's a basic just graph, right? And, simple stuff that's going on. But I added a bunch of other stuff here on the side, which you should know, especially if you're going to become a doctor. You really should know this. Or if you're taking the MCAT. Please know it, or become a nurse. So let's start out slowly, because if you're beginning your science journey, your biology journey, physiology, whatever it is, that's probably going to be the first thing you ever learn. So let's take it slow. So your body's made up of cells. Okay, we're not going to go that early, but your body's made up of cells. And the two primary ions that you need to know is sodium and potassium. So your cells, all your cells in your body are basically contain sodium and potassium. Okay? That's what does the magic here. So here we have a cell, okay? Normally, almost all cells in your body have a high concentration of the sodium ion on the outside of the cell and a high concentration of potassium ions inside the cell. So you have a high amount of sodium outside and a high amount of potassium in the inside. Ions like sodium and potassium cannot move freely in and out of the cell. It requires channels or like tunnels. So there are sodium channels and there are potassium channels. Okay, and they are required. It is required for these to exist for sodium to go in and out of the cell and potassium to go in and out of the cell. All right. You also notice something here. Don't worry about it right now. That's later. That's a problem for later. Okay. So far so good, right? Now the actual potential graph is basically a graph measuring the voltage of a certain cell, and the voltage changes based on where the ions are placed. If sodium enters the cell or potassium leaves the cell. All right, so that being said, there are two types of channels. There are sodium channels and potassium channels. Now, this is the more advanced stuff, okay? But you should know this, especially if you're in a university physiology class or you're taking the MCAT. The sodium channel has two gates. It has something called the M gate and the H gate. The M gate is located on the outside of the channel, I should say, or facing the outside of the cell. So this is the cell, right? And then this would be where the M gate is, and this would be where the H gate is. So the H gate is kind of inside the cell. It's in the channel, right? And then the M gate is on the outside, okay? And these have different properties. They're open and closed at certain times. So imagine you're driving a car and you're on a highway and there's toll roads. All right? This is what it is. This is kind of like a toll road. But the currency that we use is voltage. So it opens and closes with certain voltage. Actually, this is kind of funny. So I was in Florida like last year, and I was going to go see the SpaceX launch. So I was driving, I had a rental car, so I was on the freeway, or the highway, whatever, and then I ran into the toll road. I was like, okay, this is new, because in California, we really don't have toll roads here, toll road. I was like, okay, I pay, and I continue on. Then literally, about 2 minutes later, there's another toll road. And I'm like, so if I don't have any money, am I just stuck here between these two toll roads? What am I going to do? That's kind of like the sodium channel right here. It's gonna make a little, a lot more sense when you actually get into the actual potential graph. But that's kind of what's happening here. On the other hand, the potassium channel only has one gate. It's cheaper. This is called the N gate. And yeah, it opens and closes with voltage. So let's begin. Here we have an actual potential graph. There's a lot of things happening, but we're going to break it down very slowly. This actual potential graph is showing the time on the x-axis and the voltage in millivolts on the y-axis. So we start here called resting membrane potential. The resting membrane potential is basically when the cell is completely chill, right? Nothing's going on, nothing's happening, everything's basically completely still, right? Imagine you're a lifeguard on a beach or whatever. You just have a margarita in your hand, right? You're just chilling. You're calm, nothing's going on, right? When this is the case, we have a high amount of sodium on the outside and a high amount of potassium on the inside, like the concentrations of each ion, right? So the concentration of sodium is very high on the outside and low on the inside. And then potassium is very high on the inside and low on the outside. This is the case 99.9% of the time in all your cells in the body except very, very few places. And one of those few places would be like the inner ear, for example. But don't worry about that. That's like long time from now. When we're at resting membrane potential, aka negative 65 millivolts, the M gate is closed, the H gate is open, and the N gate is closed. So first, let's back up for a bit. The resting membrane potential, I said, is negative 65 millivolts. Sometimes in textbooks, you may see negative 70 millivolts or negative 55 millivolts. There's so much evidence, but on like what voltage it is, like people report this, other people report this. Just negative 65, it's around that range, all right? So negative 55, negative 65, negative 70, around that range, okay, is resting membrane potential. I always like to go for negative 65. That's like a nice safe space, all right? Okay, so the M gate, which is part of the sodium channel, is closed. The H gate of the sodium channel is open. So what's basically happening here is this is left open and this is closed. So if this is closed, right, no sodium can get inside the space anyways, right, because this is closed, right? If this is the outside of the cell, right, on the outside portion of the cell, and this is the inside, remember, more sodium is on the outside, so there's a higher sodium concentration on the outside. If this little gate is closed, this toll road, this is closed, no sodium can actually enter, okay? It's impossible. In addition, the N gate is closed, so the potassium channel is closed. So nothing's happening, no ions are moving because they can't. Right, this M gate is blocking the sodium channel, the sodium ions, and the N gate, the potassium channel, is closed, so no potassium ions are moving. Everything is perfectly still at resting membrane potential. All right. You'll notice the voltage slowly starts to rise here, so it's rising. Okay, this is also called depolarization to threshold. Or it's also called EPSP if you're dealing only with neurons. Because remember, neurons are also cells. We have so many different types of cells in our body. We have cardiac cells, digestive system cells, muscle cells, even neurons. There are all types of cells. But if we call it a neuron, so if we're thinking if this is a graph of a neuron, then we would just call this an EPSP. It's called excitatory postsynaptic potential. Don't worry about it. We're just going to call this rising, or depolarization to threshold. You'll notice that the voltage, right, this line is depicting the voltage, we're going up. We're going more positive. We're going from negative 65 to negative 40. We are going more positive, okay? This happens because usually the cell needs to be activated somehow. This is usually through a molecule or a neurotransmitter if you're dealing with neurons. Okay, so imagine if, let's say, a glutamate molecule binds to a cell, okay? on the outside the cell. So say we have the cell right here, and then we have cells are filled with receptors. That's something you should know. Cells are filled with receptors for different kinds of molecules, different kinds of hormones, different kinds of everything, okay? Say this is like a glutamate receptor right here, okay? So a glutamate molecule will come in and bind, okay? When something binds, right, to the cell through a receptor, this causes the M gate to slowly open. Okay, so this is a sodium channel, right? The M gate is part of the sodium channel. So it slowly opens, very slowly, okay? This causes sodium to slowly enter the cell. So let's think about this, right? I already said that the H gate was open, right? We were at resting, and the H gate was open and the M gate was closed at resting. But now, since something bound to the cell, right, bound to the receptor, this caused the M gate to slowly open. So this is now slowly opening. This causes sodium to go inside the channel and reach the inside of the cell. Okay? When it reaches the inside of the cell is getting more positive because sodium ions are positively charged. Remember, this entire graph is the potential inside the cell. It's the voltage inside the cell. So since sodium ions are going inside the cell, the voltage is going up. I know the negative numbers are kind of confusing, but just look at it. Like, it's going from negative 65 to negative 40. Right, we're approaching more zero, we're getting more positive because sodium ions are positive and they're entering the cell, okay? Imagine you're in a car and you slowly touch the gas pedal, right? Like ever so slightly. You're gonna go maybe like 1 or 2 miles per hour, but you're not gonna go zooming, right? You haven't floored the gas pedal yet. That's basically what's happening with the cell. We're kind of like teasing the cell a little bit, all right? Getting a little excited. When it reaches negative 40 millivolts, this is called threshold. What happens at threshold is the M gate is completely open now. Completely open. Here it was like partially open, right? Before we got to threshold, it was partially open. Not all the sodium ions could go in, only some. But now it's completely open. The M gate is open and the H gate is open. So basically what's happening is sodium is flooding the inside of the cell really rapidly, really rapidly, okay? Since sodium ions are rapidly going inside the cell, it spikes up in voltage because sodium is positively charged, all right? Hopefully that's making sense. This is like flooring your car, right? You're going on the accelerating ramp, you're going on the on-ramp to go on the freeway, you floor your car, right? That's what's happening here. Now, in addition, the N gate, which is the potassium channel gate, slowly opens. Why is this important? This is important because it levels off here, right? We don't want to go off into infinity, right? Infinite voltage, right? We need to control it. We have to come back down somehow, right? So this is what regulates it. So the potassium channel is slowly, ever so slightly opening. But it's not really doing anything right now, okay? It will very soon. So this is called depolarization. This spike upwards. So sodium is rushing into the cell. So now we have a higher concentration of sodium inside the cell because we rush sodium inside. Around like positive 30 or like positive 35 or positive 40, we reach the peak. At around positive 30, the H gate will close. This is the sodium channel gate, right? So this gate will seal shut. This prevents any more sodium from entering inside the cell. It will no longer be able to do that because this H gate is now closed. All right? This means that sodium is no longer going to the cell, and that means we're no longer going to get more positive. Okay? That's why we level off here, because nothing else is happening. Everything is basically completely still again. But we have a lot of sodium inside. Now the end gate is completely open now. This lets potassium go outwards. Now the question is why does potassium go outwards? The reason is because of concentration. If we have a lot of potassium on the inside, it must want to go outside by properties of diffusion. Same with sodium. The reason why sodium is going inside the cell is due properties of diffusion. It wants to go from areas of high concentration to low areas of low concentration. Outside there's a high concentration of sodium, and by properties of diffusion, they want to go inside to an area of less concentration. So vice versa for potassium, we have so much potassium inside, it feels so uncomfortable. It's like claustrophobic. So it wants to go to areas where it's less concentrated. But it couldn't until now, because now the end gate is completely open, so potassium can go outside. So potassium exits. This causes the lowering of membrane potential. So we lower in voltage. Why? Isn't potassium positively charged? Well, remember, this graph is showing the membrane voltage of inside the cell. So if potassium, which is positively charged, leaves the cell, it goes bye-bye, it kind of acts like a negative in a way, right? We're losing positive stuff inside the cell, so we're going to fall. We're going to go back down. We're going to lose voltage. And this is what we call repolarization. So the M gate starts to close, and the H gate closes. So basically, no sodium is entering the cell anymore. We're done with sodium. We're only care about potassium now, and potassium is leaving the cell because the M gate is completely open. Okay? Now we have something called hyperpolarization. Hyperpolarization, what that basically is you'll notice that this is resting membrane potential, right? This green little dot here is resting membrane potential, and this orange one was threshold. You'll notice that we go past the resting membrane potential. Why is this? The reason is because the end gate is slightly open still, and extra potassium ions exit the cell after resting membrane potential. So after we get to here, some additional potassium ions leave the cell. So since we're already at resting membrane potential here, and more potassium leaves, right? Potassium is positively charged, and it leaves the cell, we get less positive. So that's why we dip down a little bit. But at the same time, the H gate is open, right? So this kind of helps us balance things out, and we kind of go back up to a resting membrane potential here. That's what happens. Basically, the end gate is slightly open, so potassium goes outside a little bit, more outside, but then it will eventually close. Like around here, it will close, and we just go right back up to resting membrane potential. But the big question is why do we go back to resting membrane potential? The reason is because of this right here. This is the sodium-potassium pump. This is a very important topic that all cells in your body have. I also have a video on this, so please go watch that as well. The sodium-potassium pump, what it does, it always works. It's always functioning no matter voltage. It does not care about voltage. It is always on. And what happens is it pumps out 3 sodiums to the outside space and pumps potassium inside. It pumps 3 sodium outside and 2 potassium inside at the cost of ATP. And by doing this, we go back to resting membrane potential. This also answers the question, if we had a lot of sodium inside the cell, does it just stay there? Right? I never mentioned sodium leaving the cell, right? I never did mention that. I just mentioned sodium goes inside and potassium goes outside. Never mentioned about sodium, going back outside, right? How do we go back to sodium being high on the outside and potassium the inside? This happens through the sodium-potassium pump because we're shoving more sodium outside than potassium inside. So we are shoving 3 sodium ions outside, which gives us this high sodium concentration outside and high potassium concentration inside because it's always functioning. That's how. Okay, and we eventually go back to resting membrane potential. There's also something you should know. We're approaching the end of the video here, but there's something called the absolute refractory period and the relative refractory period. What the absolute refractory period means is during repolarization down to threshold, so this area right here, no matter what, we can no longer stimulate the cell. So we cannot, during this right here, going this downhill slope here, during repolarization, we cannot stimulate this cell again and have another action potential. So we cannot just go like this again, right? We cannot just spike up again randomly. That's impossible. It's called the absolute refractory period. It's basically like a protection system built into the cell, okay? Because we don't want it constantly firing. We don't want too many signals to be sent all at once. Okay, so that's what the absolute refractory period means. So no matter how much stimulus we put, so no matter how many glutamate molecules that bind to the cell, for example, if we could have 1 million glutamate molecules bind, and nothing will make this fire. We will not get another spike and get another depolarization during repolarization. It is 100% impossible. Now there's something called the relative refractory period. So during the period hyperpolarization, it's called the relative refractory period because if there is enough stimulus, so if we do have enough stimulus molecules like glutamate, then we could get another action potential. So we could indeed get another action potential like this and another one like this, okay, during this period right here. That's why it's called the relative refractory period. But we need a lot of stimulus. A lot, okay, compared to if we were just at resting membrane potential. So there's the potential of having another firing event, but we need a lot of stimulus. And that is it. If you found this video helpful, please like and subscribe. Until next time, later.